Hello students, in this lecture we are going to discuss electron spin resonance spectroscopy. Electron spin resonance spectroscopy, it is also known as electron paramagnetic resonance spectroscopy, or it can also be called as electron magnetic resonance spectroscopy. Electron spin resonance spectroscopy, it's an absorption spectroscopy where radiation in the microwave region is absorbed. And electron spin resonance spectroscopy, ESR, it is mainly used in the detection of species having one or more unpaired electrons. Those species may be free radicals, biradicals, triplet states, paramagnetic molecules, or transition metal compounds. So these are the species which can be studied using electron spin resonance spectroscopy. Now let us discuss about the basic principle behind this particular electron spin resonance spectroscopy. Electron spin resonance spectroscopy, it's mainly based on the transitions that occurs between two different spin energy levels. Now when a free radical is placed in a magnetic field, it produces generated magnetic field. This generated magnetic field can align with the applied field, it can align with the field or against the field. So there are two orientations possible for a free radical when it is placed in a magnetic field, and this alignment can be affected by the absorption of radiation. So some particular amount of radiation is absorbed, so absorption spectrum is produced. So this spectrum is known as electron spin resonance spectrum. This electron spin resonance spectrum is similar to proton NMR spectrum, but there is a difference because electron has higher magnetic moment than the nucleus of a proton. Therefore the ESR absorption occurs in the microwave region, whereas in NMR the NMR absorption occurs in the radio frequency region. Now when a free radical is placed in a magnetic field, its spin energy states splits into two different states or two different energy levels. One state with ms values plus of, another state with the ms value minus of. So in this way we are going to find two spin energy states, but these two spin energy states are degenerate when there is no magnetic field. As soon as we place this free radical in a magnetic field, these two spin energy states which are degenerate, they become non-degenerate. Now when they become non-degenerate, their energy levels or energy values are different. The energy values of these spin states are given by energy expression, which is GH beta ms. In the energy expression, the G stands for the Landé splitting factor, its value 2.003 for free electron, and beta is a Bohr magneton, its value is 9.274 into 10 to the power minus 24 joule per Tesla, and the ms is the spin quantum number for that particular state which we consider. So now when a free radical, when it is placed in a magnetic field, if it is supplied with electromagnetic radiation, it absorbs the radiations which suits the energy difference between these two states, the two states, one with the ms value plus of, the other with the ms value minus of. So any radiations whose energy matches with the energy difference between these two states will be absorbed, so we are going to get an absorption spectra. The difference between these two states with the ms value plus of and minus of is equal to GH beta. So here energy radiations having energy whose energy is equal to GH beta, that will be absorbed, so we are going to get a spectra. So since it is an absorption spectrum, we can represent in terms of absorption curve as we can find in case of UV visible spectroscopy, but in case of ESR usually we represent ESR spectra in terms of first derivative curve, as we can see on the screen, where we take the first derivative of absorption with respect to magnetic field along y-axis, and the external magnetic field applied is taken along x-axis. So this is how the ESR spectrum is represented in terms of first derivative curve. Now, if you record the ESR spectrum, any species having one or more unpaired electron, we are going to find multiple lines in the spectrum. So why do we find multiple line in the ESR spectrum, and how we can interpret? So one of the concepts that we have to study here is hyperfine splitting. So what is this hyperfine splitting? So the single line what we observe in case of ESR, that will be split due to the interaction between the electron spin and nuclear magnetic moments. So because of these interactions, the ESR signal splits. So the splitting of ESR signal, that is due to this interaction. So we are going to find many lines in the ESR spectrum, and we call it as a hyperfine structure, and this phenomenon is known as hyperfine splitting. Now because of this hyperfine splitting, or because of this interaction between the nuclear spin and electron spin, the energies of this coupled level is not GH beta ms, we need to include the interaction energy also. So the energies of coupled energy becomes equal to GH beta ms plus A into ms mi, where A is the hyperfine coupling constant and mi is the magnetic nuclear quantum number of the nucleus with which these unpaired electron interacts. So in this way we can find out the energies of couple levels using this expression. Now in order to understand what is this hyperfine splitting, we can take the example of a proton. So here we have unpaired electron which interacts with the nucleus having nuclear spin quantum number I is equal to half. Now when there is no fields, we find two degenerate energy level. When a free radical is placed in a magnetic field, its degenerate energy level splits, and we are going to find two non-degenerate energy levels. Now these two split ms states, they interact with the nucleus having nuclear spin quantum number I is equal to half. So each spin states splits into two more energy states with mi value plus of and minus of. So in this way we are going to find four different energy levels, Now we can expect, as we can see in the screen, we find four energy levels and we can expect three transitions. But here the permitted transitions are governed by one rule, that is selection rule. So here we call it as ESR selection rule. So which are the transitions are allowed, that will be decided based on this ESR selection rule. So ESR selection rule says that, so the permitted transition, in case of permitted transition, the change in ms value should be either +1 or -1, and there should not be any change in the mi value. So these are the two ESR selection rule. Based on this we decide which are the transitions are permitted. So as we can see this screen, so if we apply this ESR selection rule, we find that only the two transition, as we can see in the screen, so they are allowed as per this rule. So we find two transitions, so therefore we are going to get two lines in the ESR spectrum. And so this is the ESR spectrum for the proton. So here we find two lines in the ESR spectrum. The distance of separation between the two lines in this gives us the measurement of hyperfine splitting, hyperfine coupling constant A, as we can see here. So from this distance we can find out the hyperfine coupling constant. So in this way we are able to interpret the number of lines in the free radicals or in any species which contains unpaired electrons. So we can interpret, so based on this hyperfine splitting. So if an unpaired electron, if it interacts with a nucleus having nuclear spin quantum number I, then its signal will split into 2i plus 1 lines. So if the species contains more than one nucleus with the same I value, nuclear spin quantum number, then we can use the expression 2ni plus 1. So in this way it is possible to predict the number of lines expected in the case of species which contains unpaired electrons. So these are the aspects what we have discussed in these lectures. So we have studied what is ESR spectroscopy, the introductions to ESR spin resonance spectroscopy, and the principle behind this spectroscopy, and also the hyperfine coupling constant. So the continuation part of this we will find in the next lecture. Thank you all.